All right. So, we have a good sense, or at least a beginning of an understanding of how to deal with solutions. Okay? What we want to start to look at is different types of chemical reactions that take place in solutions. Our fundamental goal here is to get to a point where we can do some predictions. We want to be able to predict what will happen when I mix two things, when I have two different substances reacting. Okay? So, what we want to be able to do is be given a simple statement of this solution and this solution are mixed, and we want to be able to write a balanced chemical equation. Now, that's a kind of tricky process because there's kind of a lot of different pieces of chemistry knowledge that you have to put together. One of the big things that can help you do that, however, is trying to categorize types of reactions. By giving yourself some organization, some different types of chemical reactions, you can sort of imagine a decision tree of trying to predict how the reactants will form products. And so if you can say, oh, it clearly doesn't have this or this, it can't be these big categories of reactions, it narrows down what you're looking at, narrows down what the possibilities are. So, the first one we're going to look at is what we call precipitation. Okay? And precipitation is all about insoluble things that won't dissolve in water forming when we mix solutions. Okay? Precipitation is the formation of a solid from aqueous compounds, typically ionic compounds in this case. But precipitation in general is one substance changing phase in a mixture. Typically a solid forming in a solution. Okay, and we say it's coming out of the solution. The solid was dissolved in there, or the ions were dissolved. We mix them together, it changed, the reaction took place, and we formed a solid that turns into little particles and falls out of the solution. We've seen this. I did an example of this reaction with the silver nitrate and the silver chloride. If you remember, I did this example before. We had two solutions. We had a solution of silver nitrate and a solution of silver chloride. If I pour them out, if I pour them out and allow them to mix, the sodium ions, and what I need to sort of imagine is what are the new possible combinations? So the positive sodium ions are not attracted to the chlorines. That's why they dissolved into the water. They won't stick together in water. So we're curious, will they stick together with the nitrate now that I'm mixing these two solutions together? The other possibility is that the silver ions, they were positive, they didn't stick, they were not strongly attracted enough to the nitrate. Will those silver ions be attracted, will they stick with the chloride ions? Okay? And the truth is that the silver and the chloride are so strongly attracted to each other that the water can't pull them apart. And when I mixed that solution, when I did this for you earlier, we saw a white solid, this white material being created. And that white material is actually the solid silver chloride. Sodium nitrate does not react. They're not strongly attracted enough to overcome the water trying to pull them apart. So this one stays in the ionic solution. So they remain as individual ions, but the silver chloride, because of that strong attraction, form a solid. That's what we call the precipitate. The question we have to ask ourselves, the question that we need to be able to answer is, how do we know what forms a solid? How do we know whether something will be soluble? Sodium nitrate is soluble in water. Silver nitrate was soluble in water. Sodium chloride was soluble in water. They would all dissolve. They'd separate into individual ions. We call them strong electrolytes. They are substances that completely dissociate when we dissolve them in water and produce a lot of ions. Silver chloride, however, is insoluble. It does not dissolve in water. Okay? It is a non-electrolyte or a weak electrolyte, depending on if it dissolves a tiny bit, then we call it a weak electrolyte. If it doesn't dissolve at all, we call it a non-electrolyte. Or it doesn't conduct electricity. That's where we get our non-electrolytes. Electrolytes are just solutions that conduct electricity, or substances you dissolve in the solution to conduct electricity. So the question we have to ask is, there must be some way that I can tell what's going to be insoluble and what's going to be soluble. There must be some simple solubility rules that I need to memorize. Okay, they're on the Mr. Glimmy Useful Things to Memorize sheet, and these are the ones you need to know these rules. This is what we call simple solubility rules, because this is a simplification of a more complex reality that we'll talk about second semester. Okay, but so this is what we need for now to be able to make some predictions. So rule number 1, and generally the lower number the rule, so rule number 1 is generally more applicable than like rule number 6. Rule number 1, if it has a nitrate in it, if it's a compound that has a nitrate, they are soluble. Nitrates are highly soluble. Whatever positive ion you want to pair it with, it will dissolve in water. Rule number 2, alkali metals and ammonium compounds are soluble. So if it's an ion, and these are all pretty much ionic. This is about ionic solubility. Solubility of covalent compounds is significantly more complex and not applicable to this sort of thing. Precipitation reactions are generally the types of ones that we're going to deal with are ionic compounds. So alkali metals and ammonia, those are positive ions. First column on the periodic tables are alkali metals, and ammonium, NH4, positive 1 charge. We all know that. If you have those things in a compound, the compound will be soluble. It will dissolve into water. It's a strong electrolyte. No, if you have ammonium as your positive ion, or you have an alkali metal as your positive ion, so they're not going to bond together. It's either or. If you have either of those as your positive ion, it will be soluble. It will break apart in the solution to produce individual ions. It is not going to react together. Halogen salts. What are the halogens on the periodic table? Yeah, fluorine, chlorine, bromine, iodine, acetine, second to last column. We call those the halogens. Halogen salts are soluble. That is, they will dissolve in water, split apart individual ions, except if they are combined with silver, mercury, or lead. Yep, remember, those would be the positive ions. Halogens are all going to form negative ions, -1 charges. Silver chloride is an example of this rule. Chlorine is a halogen, but combined with silver, we get an insoluble compound. Okay? So these are all just observational rules. We chemists have looked at lots of different combinations and made these sort of general rules. Sulfate salts. So if it has a sulfate in it, SO4. Okay? Sulfate salts are soluble. That means they will dissolve into water, break apart into ions, unless they're with barium, lead, mercury, or calcium. Barium, lead, mercury, or calcium sulfates are generally insoluble or slightly soluble. That is, they don't dissolve very well. They form solids. Okay? Hydroxide salts. Hydroxide, that is OH minus. Hydroxide salts are generally only slightly soluble. Okay, and this is where it gets a little amorphous. That's not very soluble, generally will form solids. They'll dissolve a little bit more than, say, a silver chloride or something, but not enough for us to consider them soluble. Unless you're talking about potassium or sodium. Those are soluble. So potassium hydroxide, sodium hydroxide are soluble compounds, highly soluble. They're actually strong bases. They completely dissociate. Okay? Finally, sulfides, carbonates, chromates, and phosphates are all slightly soluble or generally insoluble. They generally do not dissolve well in water. Okay? Sulfide, carbonate, chromates, and phosphates. Notice that there are lots of things that we've left off. Those ones are just a lot more variable, and we can't easily create simple rules around those ones. So if we're doing any kind of prediction stuff, we're going to basically confine ourselves to these simple solubility rules. Again, We'll learn a way more detailed way to understand this second semester.
So when you say something is soluble, it generally means like
Dissolve
dissolving in water.
in water. This is all aqueous solubility. How well it dissolves in water. Soluble compounds dissolve in water and split apart into their ions. Insoluble or slightly soluble compounds do not dissolve in water. They stay stuck together as a solid. Okay? So, we want to be able to write down these things. These are chemical reactions. We want to be able to write them down. We know how this works. Okay? So, I can give you words. You know how to convert the words into formulas. So let's just go ahead and start with some formulas. Let's say I mix two solutions. I have a sodium sulfate, totally soluble. This is a solution where the ions are already split apart. And I'm mixing it with a lead nitrate solution. So I'm taking two separate solutions in different containers and I'm pouring them together into one container. The question is, what are the products? And there's step one is, what are the possible products? What could be formed? This positive sodium might react with nitrate. So one of my possible products is sodium nitrate. What do we know about sodium nitrate from our rules? Is that going to form a solid, or is it going to be soluble and will dissolve into the water? It's soluble. Rule number one, nitrates are always soluble. Rule number two, alkali metals are soluble. So our sodium nitrate is going to be highly soluble. We give it the AQ tag, right? This AQ here, these little ones here tell us what phase is the substance in. Solid, liquid, gas, aqueous. Aqueous means dissolved in water. So sodium nitrate is soluble, so it's AQ, dissolved in water, split apart as separate ions. We write it together for simplicity's sake for right now. What about what's my other possible recombination of these guys? So I got the lead, which could react with the sulfate. What do we know about sulfate salts? Generally soluble, except with barium, lead, mercury, calcium. So, lead sulfate is one of our exceptions that we have to memorize. See, now we put an S for solid. It is a solid, it is insoluble, does not dissolve in water, sticks together, and would form a solid that would literally fall to the bottom of the container. Okay, going to clump together in little solid particles and sink to the bottom of the container. It's going to be our precipitate. So, this is what we call the molecular equation. We have written these things together as separate, as molecules. We've written these guys together, the sodium and the nitrate, the lead and the nitrate, the sodium and the sulfate. We wrote them together. We put the AQ tag here so that we all remember that they're actually aqueous, dissolved in water. Okay? Notice that, again, the lead sulfate is not dissolved in water anymore. It's actually a solid that's precipitated out of the solution and will sink to the bottom of the container. Okay? It's in the water, physically in the water, but it's no longer dissolved. Now, what we want to do is we want to write what we call the complete ionic equation that gives us more details about what's happening. The complete ionic equation shows us if it's aqueous, if it's actually split apart into separate ions, we're going to write it split apart as separate ions. So something like sodium sulfate is actually really in the water as 2 sodium ions and a sulfate ion. Separate ions floating around independently. Same thing with the lead nitrate. Okay, the lead is a separate ion from the nitrate. Notice I took these subscripts and turned them into coefficients because there are 2 separate sodium ions floating around. There are 2 separate nitrate ions floating around. What about on my products? What's stuck together and what's separate ions? So this sodium nitrate should be written together or apart? Apart. It's aqueous, an ionic aqueous compound should be written separate sodium ions, separate nitrate ions. What about the lead sulfate? It's a solid. I want to leave it stuck together because it is literally stuck together as a solid, no longer dissolved in the solution. We call this the complete ionic equation. All we did was say, hey, if it's an aqueous ionic compound, I'm going to write it as separate ions. Literally just write them as separate individual ions, keeping track of how many there are, changing subscripts to coefficients where appropriate. Notice the nitrate still has its 3 here, because nitrate is NO3. That's the group, but there are 2 of them. We can simplify this into what we call the net ionic equation. The net ionic equation leaves out spectator ions. What does a spectator do? Watch. They don't participate. What ions didn't participate in this chemical reaction? Sodium, exact same on both sides, didn't participate. What else? Nitrate, exact same on both sides, didn't participate. So we're going to take the sodiums, okay, and the nitrates, and we're going to take them out of the solution. Okay, those sodium and those nitrates go away, and we're left with our net ionic equation. Just the actual things that changed as part of the reaction. Because they're canceling out. They have to be the exact same on both sides. Okay? Molecular, complete, and net ionic equations. So molecular, we leave things together, stuck together, kind of as molecules. Complete, separate all the aqueous compounds, separate them into individual ions. Net, take out, leave out the things that don't react, that don't change. Okay? Any questions about that process? We'll talk a little bit more about predicting stuff in the next couple of days.
So the bottom one you call the net equation?
Net ionic equation.
So the one above that would be
Complete ionic equation. We call it the complete ionic equation. And we call that the molecular. I know the financial metaphor breaks down, but we're not in a finance class. So. Okay? All right, give this a shot. Your turn. Solutions of potassium sulfate and lead-4 nitrate are mixed. Right? Balanced molecular, complete, and net ionic equations for the reaction. Please, once again, note, if you don't know what the word sulfate means, if you don't know what the 4, Roman numeral 4 means, or the nitrate is, you need to go back through and rememorize those things, because you will be stuck on these problems without those words. Okay? All right, give those problems a shot. About ready to look at this? Yes. Molecular, complete, and net. He had the net. So step 1, you've got to convert these words into formulas, right? So, potassium sulfate. Why did I put a 2 here for the potassiums? To balance what out? The charges on these ions have to sum to 0. When I'm writing the molecule, when I'm writing down the ionic compound, I balance out those charges. Okay? So my potassium sulfate has to have 2 potassiums to balance out the -2 sulfate. Same thing here. Lead 4, the Roman numeral 4 tells me it's a +4 charge, which means I need 4 of the -1 nitrates to balance it out. Now, when you're writing these compounds, you think about these charges. When you're coming over to the other side, to the products, and saying, hey, the positive here could potentially react with the negative here, let's write down what that compound would look like. You worry about the charges in this molecule. The reason we wrote a 2 here was because sulfate had a -2 charge. Nitrate only has a -1 charge, so I put 1 potassium. +1, -1. Don't carry over the subscripts from there to here because it's going to mess everything up. The reason you put the 2 here was to balance out these charges. The reason I didn't, the reason this is a 1-to-1 is because that's how you balance out these charges. Lead, the positive from the lead nitrate, could potentially react with the -2 sulfate. +4, -2, that means I need 2 sulfates to make this balance work. And then I go through my simple solubility rules that say, hey, sulfate compounds are generally soluble except with lead. So this gets the solid. Rule number 1, nitrates are always soluble. Rule number 2, alkali metals are always soluble. So potassium nitrate is soluble, aqueous, AQ. That means it's soluble, dissolved in water. I balance the equation. I know I needed to have, here I had 4 nitrates, which means I got to have 4 nitrates over here. I put a 4 in front. 4 potassiums means I got to put a 2 out in front here. That also solved my 2 sulfate issue. Okay? Step 1, write down what the molecules are. Write down what the new products could be. Figure out, using the rules, whether it's aqueous or solid. Balance the chemical equation. Again, in general, look at polyatomic ions, nitrates, sulfates as one thing to balance. It's going to be easier. Okay? So I balanced the sulfates. I didn't try and balance the sulfurs and the oxygens. I balanced the sulfate as a group. I needed 2 of them. I put a 2 out in front there. Now, anything where it says aqueous, if it says AQ, aqueous, it's an ionic compound, what do I do to it? Break it apart into its ions. And whatever the coefficient is, that coefficient needs to be taken into account as well as the subscripts on these individual ions. So I'm going to break these apart. 2 and 2 is 4 potassiums, 2 sulfates, 1 lead, 4 nitrates. Remember that nitrate is NO3, but there's 4 of them from that subscript there. Solid stays together, unchanged, just drop it straight down. Aqueous, broken apart, 4 potassiums, 4 nitrates. Now I say, hey, what are my spectator ions? What sat around and watched? What did not change? Cross out the things that didn't change. Potassium doesn't change, and nitrate doesn't change. And I'm left with my net ionic equation. So when the things are separate, you must show the charges because they are ions. When you write them together, you must not show the charges because the charges are canceling out. So individual ions must have charges. Ionic compounds should not have charges because the charges are canceling out.
If we get this on the AP test, do we have to do all 3 of them?
No, on the AP test, they ask, in general, for the net ionic equation. Now, unless they specifically ask for something else, you can assume they're asking for the net. And in fact, in the question where we see this most often, they specifically ask for the balanced net ionic equation. Now, we'll go over that. I'm going to give you a bunch of practice sheets in the next couple of days. We need to learn, there's 2 more types, general categories of reactions we need to learn. Acids and bases, and oxidation redox reactions. Oxidation reduction reactions. Then we'll have all the pieces. We can start trying to say, okay, here is a set of reactions for you to try and predict what's going to happen. As a whole sort of separate skill, but you got to have this base understanding of what happens. All right? All right, homework for tonight. (29, 31, 35, and 43). Okay? That's your homework for tonight. Please do. Yeah, they're on the cart.